Okay, hello everyone. I will represent the first step in our solution on the quantum chain problem, where we would try to figure out what is optimal way to distribute vaccines. The way we solve this problem is using D-Wave, and we are optimizing using impact value function, which determines what is the impact of vaccinating a particular group of people and how this contributes to well-being of the remaining group of people surrounding them and their co-workers. Of course, the first group to be vaccinated should be the front line workers, health workers, and people in hospitals. Here we run a simulation where we assume that about 50,000 vaccines will be the first batch to be distributed in the United States. This could be adjusted as the time of distribution comes around. And when it is done, basically we try to maximize the number of impact value. And in our solution, we consider about 100 cities. Again, this number could be adjusted. And when a city is in the list of knapsack, that means that they will receive vaccines for their clinics and hospitals to be distributed there. And if the city is not in the knapsack, that means that in this distribution, vaccine was not distributed to these other cities. Now, with this kind of optimization problems, the more complicated they are, the harder it is to find the best solution. So there is a list of possibly good solutions that could be different in which cities are receiving vaccine and which are not. What is important is actually how the capacity of the vaccine is utilized and what is the impact value when this population is vaccinated. Of course, even if people are not receiving vaccines, this is still a positive impact value from the sick people in the area that are in these hospitals, because they're still kind of receiving immunity. So we have an option where we can run with non-zero values knapsack with a value of like 1% and 2% weight of how this would contribute to the impact of overall fighting of the pandemic. Now, once a particular list of cities and solutions has been decided upon, and here's an example of these 100 cities and their distribution that we considered, we can break it in region where the vaccine will be distributed. And from these distribution centers, we do calculations of what is the optimal route to distribute the vaccine. We use again D-Wave and quantum computing algorithms to do these calculations. Here's an example where we consider a case where there are about 20 cities out of the hundreds in the United States that will be distributing something and finding what is the optimal route to go to these places. This is just illustration and validation that the algorithm works. For practical purposes, we also did calculation for California. So we selected San Francisco to be a distribution hub with few cities around San Francisco, and then we are assessing what is the optimal path to distribute the vaccine. This is only the first step. In the next steps, we will be looking for other opportunities and changes that would have to be done. And Tina would explain how we selected the sub-regions and distribution hubs. So this is for the very first stage of identifying which cities would receive vaccines, and then how do we simulate the distribution.
We have combined a clustering algorithm and a traveling salesman problem solution to dynamically calculate the shortest route to follow to deliver vaccines most effectively. The quantum clustering algorithm will identify and group the different destinations into clusters using the geographic latitude and longitude coordinates to calculate the distance between them. We formulated the clustering problem mathematically in binary quadratic model format, BQM format. The key properties of the clustering problem that we try to capture are 1. Each vaccine destination can only be part of one cluster. 2. Data points that are close together should be part of the same cluster. And 3. Data points far apart should be in different clusters. The traveling salesman algorithm is then applied to each of these clusters individually to calculate the shortest route possible to cover the number of cities in this cluster. The output of this solution has been plotted to a map with the starting and ending points coinciding and alternate best routes calculated for different scenarios. This will help to rebalance and reroute the distribution. And if vaccine efficiency or product quality are affected, then this enables us to assess alternative nearby delivery locations that will maintain the maximum impact solution that we discussed earlier and proceed with the updated delivery schedule. This solution can also be used for ensuring that PPE and COVID tests are also distributed to the medical centers along with the vaccine distribution. So we now look at the solution that we're going to run on D-Wave. It uses a QB solver and D-Wave, and we have functions for getting the distance and calculating the maximum distance, which will help us to cluster the points. And then we plot it, but not before we run the traveling salesman on top of each of the cluster. So when we run it in D-Wave, we're waiting to have the most efficient routes generated. As you can see here, the D-Wave problem inspector has kicked in. And you can see the different route maps generated here as well as the clustering diagram. Energy has been minimized, which is basically the distance between the different cities in the cluster. And to see the output of the algorithm, this is one route. This is an alternate route that will be calculated if we need to. And this is another route that will be calculated. And this is a visualization of the clusters generated.
Here's a quick overview of the dashboard that allows you to efficiently track the status and location of your vaccination shipment. The green dot shows the current location, while the red dots indicate stops along the route. You can monitor the conditions through this chart, which presents the sensor reading, updated every 10 minutes.